In this next section, section 4, introducing LANs, we're going to be talking about really what is a LAN, what are some of the components of our local area network, mainly switching, right? Switching is certainly we have routing in our LANs, but switching is a major component to the LAN architecture because it allows us to create those endpoint connectivity options for our devices to be able to connect to the network. Right? But a local area network by definition is really just a high-speed network that allows us the ability to interconnect our devices locally, as opposed to a WAN, which is something that where we're connecting devices through the internet or connecting devices over a service provider managed network. So what we want to make sure that we understand in this particular section is what is a LAN, what are the components of the LAN in our topology, why do we need switches as opposed to hubs, and what are some of the switch characteristics? In other words, how do switches function, how do they learn, how do they make their decisions, and so on. So this is a pretty important concept. Now, with regard to the LAN itself, it's a pretty, obviously a pretty basic concept. Basically, a LAN is just a bunch of interconnected devices under a single management domain. And it doesn't mean that we're not doing routing. We could still be doing routing. We could still have VLANs. We can still have separate broadcast domains and separate types of devices. And it can be a small network or it can be a large network. But the contrast to a WAN is that most LANs are managed by your internal organization. They're typically going to have higher data speeds. They're going to cover a smaller geographical area. You're not going to have some service provider managed connection and so on, where the WAN provides us connectivity options over large geographical spaces, whether it's in a city, across the country, across the globe, whatever it might be. And we have our TSPs, our telecommunication service providers. They call them TSPs now because they do more than just provide internet access, but these telecommunication service providers provide us the ability to interconnect our locations with various circuit options, as well as maybe even privatized circuits like MPLS, layer 3 VPNs, or frame relay or ATM or whatever it might be. So the typical components that we would see in an enterprise LAN, of course that's going to include switching, right? It's going to include switches, and these can be just basic layer 2 switches, or they can have some intelligence built into them. They can have some layer 3 functionality. Those are what we call multi-layer switches. We'll talk about that a little bit later on. We're certainly going to have some physical layer components as well, the cabling and the interconnections between the different devices. We're going to have our hosts and our endpoints. We're going to have all of our other network devices as well, which can include maybe a wireless LAN controller, some access points, some routers, and so on. But the idea is that we have really just all these devices connected together. What types of protocols would we typically see in a LAN? We're going to see some sort of switching protocol, right? Either Ethernet 2 or 802.3 Ethernet as a LAN switching protocol. We're going to see some sort of network layer transport protocol like IPv4 or IPv6. We're going to see probably some transport layer protocols as well, TCP and UDP. We're going to see some client application protocols that are necessary for the clients to participate in the network. Things like ARP, the Address Resolution Protocol, which we'll talk about a little bit later on. DHCP, the Dynamic Host Configuration Protocol, or maybe even DNS, the Domain Name System, or Domain Name Service. And we might see some other things like CIFS and some Active Directory protocols and so on. But obviously the idea is that we have to manage these protocols, we have to manage the data, we have to manage the applications, we have to manage the resources. And that includes providing those three cornerstones of communication that we talked about on day number one, right? Confidentiality, potentially. Now, that doesn't necessarily always mean encryption. It could mean some sort of network segmentation in the form of VLANs or private VLANs, or maybe some sort of network attachment security like 802.1x or port security or something like that. Integrity, not so much. We don't typically implement integrity protocols within the LAN unless it's part of an application. But certainly availability is a key component, right? We want to make sure that the resources are available. So we'll talk about all the protocols that we can implement in the LAN, but we're also going to talk about the ways that we can implement our LANs more efficiently to provide that redundancy and those redundant connections and so on. All right? Now, why do we have switches? Back in the day, we used to have these things called bridges, and prior to that, we just simply had hubs, right? We know from our discussion yesterday about the different, the OSI model and the different types of devices, that a hub operates at layer 1. So let me talk about that real quickly, because I know this is a basic concept, but I want to make sure that you guys understand. When it comes to a hub, even though it might physically look like a switch, when you have a hub, let's say I've got this device and I've got 5 devices or 5 components or PCs attached to that particular device, and this is a hub, right? There's 2 things that we consider when we're talking about efficiency within the network. What is the size of the collision domain, and what is the size of the broadcast domain? A hub doesn't create any separate collision domains or separate broadcast domains. So let's say, for example, if this device here is transmitting information into that hub automatically is simply going to duplicate all of that information out of every interface, regardless of whether or not those devices need to hear that information and so on. Now, if for some reason this device tries to transmit at the same time, that is going to cause a collision, meaning that the data is going to get corrupted. And then what happens is we do a back-off algorithm, and everybody has to stop communicating. That, by the way, is something called CCNA CD, right? Carrier sense with multiple access with collision detection. Carrier sense means this device and this device and this device and this device, they're monitoring their network interface to see if anybody is transmitting. The idea being that if somebody's transmitting, I'm not going to transmit at the same time. Okay, I'm not going to transmit at the same time because I know that it's going to cause a collision. If a collision occurs, everybody, a jamming signal gets sent across the whole device, and then everybody has to stop transmitting. Everybody starts their own random timer. So this guy has a timer, this guy has a timer, this guy has a timer. And whoever's timer expires first, they're allowed to transmit. Everybody else has to kind of wait. The problem is that these collisions occur all the time. So every time a collision occurs, the network has to stop functioning. This is what we call a collision domain, meaning that every device is in a common collision domain. Subsequently, obviously, it's a single broadcast domain as well, because if one host sends a broadcast, everybody else is going to get that broadcast. Now, what if I replace this device with a switch? All right. Now, switches operate at layer 2 of the OSI model, but there's a couple of things that make a switch more efficient. Actually, let me not do the switch yet. Let me do a bridge. This is the typical symbol that we use to draw a bridge. We don't really see bridges anymore, but when I started doing networking back in the mid-90s, late 90s, this is how we added efficiency to our networks, because we had our hubs, which are usually just drawn with a single arrow, and what the bridge allowed us to do is to have a separation of these collision domains. So this is a layer 2 device, just like a switch, and it has intelligence. It learns MAC addresses, just like a switch does. So it will learn all the MAC addresses of these devices, A, B, C, D, and it will learn the MAC addresses of these devices, E, F, G, and H, and it will actually put that into a database. And if A is sending a frame to B, even though that data is being duplicated on this interface, because A and B exist on that interface, it blocks that traffic from going over to that side of the network. All right? In other words, it's making an educated filtering decision, and it's filtering the traffic from being sent over to the other hub, which means that host E and F can talk to each other at the same time A and B can talk to each other. And that's basically what a bridge did. We still had, larger collision domains, but the bridge allowed us kind of more efficiency with bandwidth as long as the traffic was localized. The difference between a bridge and a switch is not that much. The bridge typically had fewer ports because it was only creating, a couple of different segments or whatnot. But also the bridge did everything in software. It didn't do anything in hardware, so it wasn't as nearly as efficient as a switch was. All right? And, it's still one broadcast domain, by the way. All these clients are still in the same subnet. So if client A sent a broadcast, it would go all the way across the network. Now, what if I replace this with a switch, which, by the way, is just called micro-segmentation? I actually saw that on somebody's resume one time. They said that they were responsible for the micro-segmentation of the network. What does that mean? Oh, we replaced all our hubs with switches. Okay, that's great. Good job. All right. That's the term that they use to describe that. So now we've got this switch. Now we've got our individual ports, and we're gaining even more now because this switch is an intelligent device. It still operates at layer 2, but now it does it in hardware in the form of ASICs, an application-specific integrated circuit. But it's learning the MAC addresses of these devices based on the port number that they're attached to, and it's creating a database in Content Addressable Memory, CAM. That database is called a MAC address table, and it's mapping the address of the client to the port. And what a switch does, and it does this passively, by the way. What do I mean by that? The switch doesn't actively go out and try and figure out who's attached to what port. It just simply waits for traffic to flow. Once traffic flows through a port, then the switch will update its database. So in the beginning, a switch kind of acts like a hub. All right? There's actually only two decisions that a switch makes. Am I going to forward the traffic, or am I going to flood the traffic? Those are the only two decisions a switch ever makes. Now, again, we're not talking about VLANs here. We're not talking about adding access lists or any kind of filtering. Fundamentally, these are the two decisions that a switch will make. Am I forwarding the traffic, or am I flooding the traffic? When do you think the switch might flood the traffic?
If it doesn't have a port assigned to that MAC address already.
If it hasn't learned the destination, right. So initially, all the traffic gets flooded until the switch starts to learn and starts to update. We're getting a little bit ahead of ourselves. Obviously, this is the whole point of this section, but I don't want to overwhelm you too much with too much information, even though this is stuff that you probably already know. But the switch is an intelligent device. But it's more than that, right? Let's say, for example, client A wants to send data over to client D. No problem. The switch recognizes, let's say the switch has already learned everything, so it internally switches that traffic, and that traffic goes down to D. At the same time, let's say B wants to talk to C. Well, guess what? That switch can then forward that traffic to switch C. So we can have multiple conversations at the same time occurring, which is much more efficient without having the collisions. In fact, every single interface on the switch is considered to be its own separate collision domain. That has also to do with the fact that we're running what we call full duplex communication as opposed to half duplex communication. We'll get into that a little bit later on. But switches are even more intelligent than that, especially a Cisco switch, because Cisco switches actually do everything in hardware. So they're basically switching traffic at wire speed. But let's say client A wants to talk to B, and at the same time, client D wants to talk to B. And let's just say they both happen to send the data at exactly the same time. Well, now we have a bit of a dilemma, right? Because I can only process one frame at a time down to B. I can't send both frames at the same time. Well, the switch has built into it buffers to store information. So it can actually say, okay, I'm going to go ahead and store this one in memory. I'll go ahead and process this frame and send it down to that client. And then once that frame is done being processed, I'll then go ahead and send that frame down afterwards. So the switch is very, very intelligent. It can make very, very intelligent decisions. It's a really basic device. You know, it's kind of a plug-and-play type of device. I mean, assuming you're not enhancing the configuration with a bunch of other things, it's really just a basic plug-and-play device that has the ability to learn and make decisions. All right? So let's go back to our text here. The other reason is the segment length. Now, in Ethernet, we have a limit to how large or how long an Ethernet segment can be, and that is 100 meters. I think that's what, like 300 and something feet, right? 100 meters is the distance limitation for an Ethernet segment. But that's per port, right? So this cable here can be 100 meters, that cable can be 100 meters, that cable can be 100 meters. So we can actually also use a switch as a kind of a repeater, if you will, to extend the length of a segment or to extend the overall path. We used to do this in the old days with an actual device called a repeater, but there was a limitation as to how many repeaters you could put in one segment. You could only have up to 3 repeaters in a segment because the repeaters are layer 1, which means you're still creating that very large collision domain. With a switch, we don't really have that limitation. You can have 4 or 5 or 6 or 7 switches in a row because they're making intelligent forwarding decisions, not unintelligent forwarding decisions. All right? So the switch operates at the data link layer, at the, what they call it the link layer of the TCP/IP model, what we call the data link layer in the OSI model, but it's still layer 2 device. And as I described, it selectively forwards individual frames, but only after it's learned, right? It still has to learn everything. So initially a switch will flood all the information until it starts to learn. There is a type of attack, and it's a little, again, beyond the scope of this section here, but we'll go ahead and discuss it. There's a type of attack that you can propagate against the switch to turn it into a hub, and it is called a CAM overflow attack or a MAC flooding attack. And the whole concept of a MAC flooding attack is that I attach the device to the switch, my computer or whatever device I'm using to attack that network, and what I do is I start flooding in a bunch of bogus, let me get back here, I start flooding in a bunch of bogus frame information. So maybe thousands and thousands of frames with different MAC addresses. The idea is that I'm filling up that database, that MAC address table. I'm filling it up with a bunch of bogus information so that if somebody legitimate sends a frame, there's no more space in that database to store that information. This information is stored in memory, right? So we're making forwarding decisions in hardware, but we're still storing the database in memory, and there's only a finite amount of space to store that information. If that MAC address table gets full, we don't just simply replace the oldest entry with the newest entry, like first in, first out. We just don't put any new entries in. So D, all of D's traffic in this particular case, because D's MAC address can't be learned, all of D's traffic ends up getting flooded, and now I can open up Wireshark and I can capture that information and I can see that data, right? There are ways to prevent this. The most common is to do port security, but there's some other mechanisms you can use to prevent these CAM overflow or MAC flooding attacks. Does anybody happen to know how long information stays in the database? Once I've learned a MAC address, how long does it stay in there? By default, it's 5 minutes or 300 seconds. So if D was learned on that port, that entry will stay in that CAM table or that MAC address table for 5 minutes. If D doesn't communicate after 5 minutes, then it will get flushed. You can adjust that timer. I don't usually recommend it, and I don't think there's really a whole lot of need to do it, but you can adjust that timer value. But again, it's not an infinite amount of space to store information. And the switch still does what it does. If it doesn't have any more space to store information, it just simply doesn't write that information to the database. We have lots of ports, which allows us to segment a large network into many smaller segments. What they're referencing in that particular case is the collision domains that we talked about. Remember I said the term is called micro-segmentation? We're taking a large collision domain and we're making a bunch of small collision domains. That's basically what they're referring to in this case. All right? The main purpose of a switch is to forward frames as fast and efficiently as possible. Absolutely. And this is probably a little bit beyond the scope of this. Again, I keep saying that, but I doubt that this is actually even in the content. So I'm going to actually talk about this as well, because I think this is important as well. All right? So if you look at an Ethernet 2 frame, all right, and we will in Wireshark a little bit later on, it has a preamble, it has a start of frame delimiter. Those are not really technically part of the frame itself. They're basically just synchronization bits and bits to indicate to the client at the physical layer that the frame is coming. Destination MAC is the first field. That's 6 bytes. All right, and I'm talking about Ethernet 2 because pretty much Ethernet 2 is what we use. We have the source MAC, which is another 6 bytes, right? And then we have our type field, which is 2 bytes. You guys remember what the type field was for? We saw that in Wireshark yesterday, right? It's to identify the next header. Basically what's coming at layer 3, okay? And then we have our payload field, which is anywhere from 64 to 1500 bytes. And then we have our frame check sequence, which is our cyclic redundancy check. That's for our integrity check, and that's 4 bytes. All right? So that's basically what our frame looks like. And the reason I bring this up is because it's a pretty basic header. There's only really 3 fields in the header, and only 2 of the fields matter to the switch, destination MAC and source MAC. Now, technically, what does the switch use in this header to make an actual forwarding decision? What does a switch use in the header to make an actual forwarding decision? Destination MAC. Where is the frame going to? Which happens to be the very first thing in the frame itself, isn't it? What in the header does the switch use to make a learning or to learn? Source MAC. So it's a really, really simple concept. This frame arrived on this port. This is the source MAC. I'm going to map that MAC address to that port. Is the destination MAC address in my database? If it is, I'm going to forward the frame to that port. If it's not, I'm going to flood the frame out of every port except for the port that the frame came in on. All right? Now, the reason I went off on this little tangent is because in Cisco's world, there are three primary forwarding methods that switches use. I'll just leave that off. All right? There's what we have store and forward switching. All right. In fact, let me get rid of a couple of these things up here so I can, all right. There is cut through switching, and then there is fragment free switching. Man, I cannot type today. All right. So store and forward switching, what do you think the name indicates? When you think of switching, what do you think store and forward represents? Process and store the entire frame from the destination MAC to the FCS, and then make your forwarding decision. Make sense? Store and forward. Okay? Slow. Very, very slow switching method. But what is the benefit of the store and forward switching method? We can check the integrity of the frame, right? Because I'm actually processing the frame. Before I make a forwarding decision, I'm processing the frame all the way up to the frame check sequence, which means I can do the cyclic redundancy check, which I'll talk about. I know we haven't talked about that part yet, but it's just a way to verify that the frame hasn't been corrupted or modified in any way. And then I can make my forwarding decision. You buy an off-the-shelf switch from Walmart or Target or Best Buy or whatever, most likely it's going to be a store and forward switch. It's not going to have any kind of real intelligent, it still functions basically the same way. It's probably unmanaged, but it doesn't do any kind of other switching method. Cut-through switching. What do you think cut-through switching does? Cut-through switching means that we make our switching decision as soon as the first 6 bytes are processed, right? So very fast, because we start forwarding after we see the destination MAC. I mean, really, that's all I need to see to make a switching decision, isn't it? Where's the frame going? So cut-through switching is the fastest switching method, but what's the downside to this method? You could be forwarding bad frames, right? Could be forwarding fragments, or you could be forwarding frames that the integrity hasn't been maintained and it's a corrupt frame. You could be forwarding. Doesn't mean you're not actually necessarily forwarding bad frames, but you could be. But it's definitely the fastest switching method. And ultimately, that's always been the goal of most vendors, is to try and switch data as quickly as possible. Wire speed switching. All right? And then we have fragment free. So this is kind of something that's unique to Cisco. It's kind of a mix of both. All right? Correct. So what we're going to do with fragment-free switching is we're going to process the first 64 bytes of data. Now, why 64 bytes? Well, Cisco calculated that most collisions and most fragments occur within the first 64 bytes of the frame. So if I've accumulated 64 bytes of a frame, most likely, we still can't verify the integrity, but most likely it's a complete frame. It's not guaranteed, but most likely it's a complete frame. So it's kind of a mix of store and forward and cut through, where we're not storing the entire frame. It's actually much closer to cut through because we're only doing 64 bytes, which is really pretty much just the header information if you think about it. You've got 12 bytes well, actually 14 bytes of the frame header. Then you might have a 20 byte IP header, maybe a 20 byte TCP header. So you're really talking about processing all the header information before you decide to start forwarding the frame. All right. All right. So I just wanted to mention that as part of our discussion here because I do think it's relevant. There are different types of switching methods. Ultimately, though, it still boils down to two decisions. Do I forward the frame or do I flood the frame? And by the way, if I do flood the frame, I never send the frame back out the same interface that it came in on. We never do that because that would create a loop in the network. All right? So we have the ability to buffer. We're operating in full duplex mode. It's dedicated communication. Let me go to the graphic here. Dedicated communication between the devices. We can have multiple simultaneous conversations. We can do media adaptation, or rate adaptation. And actually, we can even do media conversion, right? Because switches can have fiber ports, they can have copper ports. We can use SFPs, small pluggable form factor adapters, basically, that allow us to change from a copper interface to a fiber interface. So we have all that capability. All right. Now, there are different types of switches that exist with Cisco. There are what I would refer to as stackable switches, and then there are chassis-based switches. So if I did, for example, Cisco 6500 series, these would be an example of a chassis-based switch, right? This is kind of a whole line of them, if you will. And there's many different kinds, but the chassis-based switches are nice because you can have multiple line cards. Those line cards can provide different functions. Some of them can be fiber concentration cards or twisted pair Ethernet cards. Some of them can be route processors. Here's an example. These two right here are route processors. Here's an example. These are kind of older switches, but you get the idea. You've got this whole fan module on the side for cooling. You've got redundant power supplies and all kinds of things. These are great switches, but there's a pretty heavy footprint for these switches. I mean, they require a lot of power and so on. So smaller companies don't necessarily need that, right? Oops. Smaller companies don't necessarily need that. So you would have like a Cisco 3850 switch, which is what we would consider a stackable switch, what I call a stackable switch. Stackable switches have fixed configurations. So you would see, these, let me go back to images here and just pull up this image. So these are like your fixed configuration switches, 1U or 2U switches, and they have fixed port configurations. Maybe they have some interfaces here that allow you to connect different types of interfaces based on the, what we call an SFP, right? It's a little pluggable module that allows us to change the type of interface that it might be. All right? But Cisco actually took it one step further. It's not new. I mean, Cisco didn't invent this technology, but they've certainly perfected it, where they have something called Stackwise and PowerStack. And what they did is they said, you know what? Let's try and come up with a way of creating a chassis-like environment with a stackable switch. So they've got these proprietary physical layer connections on the back that allow you to create this ring. You notice here it goes port 1 to port 2, port 1 to port 2, port 1 to port 2, and then port 1 all the way back up to port 2 on the first switch. So we're actually creating one logical switch from 4 separate physical switches. Does that make sense? So this now becomes like a chassis. You don't have 4 separate command line interfaces. You don't have 4 separate management addresses. It becomes one logical switch, and when the clients want to communicate to each other across the switches, they communicate across this backplane, which by the way operates at hundreds of gigs. Not like 1 gig or 2 gig. It's in a 3850 stack, it's 480 gigs of throughput. And then some of the newer switches, the stacking is even faster. They also extended that to the power system as well. These are actually power cables or power stacks. And so if these 2 power supplies fail on this switch can draw power from the other switches to maintain its status. This is what we're talking about when we talk about high availability, right? That availability concept. So it's much more than just these basic boxes here. There's a lot of things that we can do with switching today that we couldn't do in the past. What is the difference between half duplex and full duplex communication? Half duplex means you can send and you can receive, but you can't send and receive at the same time because it will cause a collision. Hubs typically generally operate in half duplex mode, whereas switches operate in full duplex mode. We have a transmit path and we have a receive path on the pairs, and they're separate paths, so the data can flow back and forth without having a problem. Okay? So they have a pretty picture here, kind of like the one I showed you, the 9000 series. If I pull up the 9000 series, actually let me do a quick search, and let's do Catalyst. By the way, Catalyst, you see that from when you look at all the Cisco switch names, they always say Catalyst. That's because that's where Cisco bought the technology from. It was a company that actually came up with that name originally. Catalyst 9000 series stack speed, or stack ring speed. I just want to confirm what the ring speed is of, I think it's in the gigabit range, if I'm not mistaken, not the megabits or hundreds of megabits range. But again, this is a chassis-based switch. The nice thing again about the chassis, you've got this removable fan tray here. So if you have problems with the fans, you can replace them. Fans are kind of one of those types of components in a chassis that have a very low mean time between failure rate or high failure rate. Here's all your power supplies. It looks like, or actually these are hard drive bays for UCS type stuff, computing system stuff. These are your route processors, and then you have your switch modules and so on, and then the power supplies are in the back. But again, you have the capability of stacking these switches as well, and you can get different types of switches based on, what your needs are as far as the, so it's still only 480 gigs. Okay. Yeah, I knew it was in the gigabit range, but that's the same as the 3850. So you can create these stacks, put 9 or 10 switches together in a stack and so on. Actually, not 10. It's usually 9 or fewer. All right. But the benefit of these switches, high port density, right? Lots and lots of interfaces, large buffers. Now, we want to have those large frame buffers because we have lots and lots of data flowing back and forth to an interface. And oftentimes we have, potentially hundreds of frames going to an individual interface at one time. We have to be able to store that information. Also, port speeds are pretty diverse as well. 40 gigs up to 100 gigs of speed. So very, very fast and relatively cheap. Not cheap, but relatively cheap as far as per port cost. The unique thing about Cisco, Juniper does this as well. But the unique thing about Cisco is their ASIC technology. An ASIC is what we call an application-specific integrated circuit. It's basically a programmable EEPROM that allows us to identify a particular function for that particular chipset. So we can, ASICs are used in all kinds of applications, even outside of Cisco and other vendors, but having them to be, making them programmable is something that's kind of unique to Cisco and Juniper. And that's where software-defined networking comes in, and the ability to change the function of a device on the fly in hardware. That's a pretty amazing thing. All right, but these general purpose CPUs and these ASICs and whatnot provide the ability to do wire speed switching, and that's really the claim to fame from Cisco's perspective, is that we have that ability. All right, so that is pretty much the end of that section. It was a pretty basic section. We'll wrap that up, and then we're going to get into kind of more details about the TCP/IP layer in the next section.